late. Okay, so Leonard just asked, why is the dimension of A in degree m equal to the dimension of A, sorry, what was it? A in degree m is equal to A reduced in degree m plus the dimension of A m minus 1, right? Is this the identity that we had there? I think so.
Leonard says no, I think.
Wait, sorry. A in degree m. Yeah, no, I think this is it.
So I thought it should be the dimension of the space spanned by the primitives of AM.
No, but the primitives have no
Okay.
such simple law. I mean, maybe you look only at small degrees, and at small degrees there is a simple law. But there isn't a general law. There isn't something so simple with primitive. For the primitive, the dimensions will be the dimension of the polynomial ring, and you can compute it by enumerating all possible monomials in the primitives. But it's not such a simple formula. There might be more efficient ways to compute it, but again, it's not so simple. But this is simple. So basically, these are, and in fact, I promise that something like that will be in the homework, and it will be, but a different versions. But these are polynomials in theta, where theta is the chord diagram with one chord, right? So these are polynomials in theta and all the other variables, x, y, etc., all the other primitives. These are polynomials with no theta, because you mod out by theta is equal to 0. And these are polynomials of degree 1 less in all the variables, so theta, x, and y, theta, x, y, etc. And then this equality is kind of clear, because if you have a monomial, okay, so let's count dimensions. So if you have a monomials in all of the variables, if it has no theta, it falls in here. If it has a theta, divide by theta, and you get a polynomial in degree less, in 1 less in all of the variables. Okay, so it actually is clear. Okay, now let's start with the actual content, or what I was going to do today. So let me remind you that en route to relating finite type invariants with Lie algebras, I wanted to prove an intermediate theorem. So the space of chord diagrams A modulo 4T relations. So just to remind you, this A is chord diagrams modulo 4T relations. I claim is isomorphic to A trivalent, or a temporary, which are diagrams like this. So they have a skeleton, which is a circle, and then a trivalent graph inside. And the graph has to be connected. The vertices are oriented, which means that on every vertex you specify either one of the two possible cyclic orderings of the edges on it, and the convention is that if not specified, it's as drawn in the plane, going counterclockwise. And here there is also a degree. The degree is 1/2 the total number of vertices. And here we mod out by three relations: antisymmetry, which is written here, STU, which is written here, and IHX, which is written here. And in fact, it's a bit of a lie, because these two relations, the antisymmetry relation and the IHX relation, are redundant. The isomorphism holds even without them, but I put them in because it's convenient to remember them as in one block. Okay? So you'll see later they're implied. Okay? Anyway, why is this theorem true? So the theorem is actually very easy. Well, with one tiny minor complication which we will resolve at no time at all. So basically, in order to construct an isomorphism between two spaces, you have to construct a map going one way, let's call it phi, and a map going the other way, let's call it psi. Okay? So phi, so again, let me just sort of copy to here. So A and A with trivalent vertices, and I want to construct a map phi going this way and a map psi going the other way. So phi is completely trivial. So phi is the map which maps every chord diagram. So here you have chord diagrams with no trivalent vertices, but you can always map every chord diagram to itself, to a graph with no trivalent vertices. The only thing to verify is that it descends modulo the relations. So here you have the 4T relations. You have to make sure that the 4T relations go to 0 here. But this follows from a very, very, very simple picture. And here it is. So suppose you have a, maybe I didn't leave enough space. So suppose you have a graph. This is in A trivalent, so it has one trivalent vertices, and it may have lots of other junk. The other junk I'm not drawing, so I mean there may be more stuff, but I'm not bothering to draw the more stuff. Okay? But now this diagram in AT, so I'm going to write an identity in AT. So in AT you can reduce it modulo STU in two ways. You can reduce it around this edge. So if you look, so maybe I'll remind you what STU was. So STU was that if you have a Y sitting on the external skeleton, you can reduce it to two parallel lines minus two cross lines. So if you have so here you have a Y sitting on the skeleton. So I can reduce it, and I get two parallel lines minus two cross lines. On the other hand, I could have reduced it in this direction, which would take standing like this and looking, and looking upside down, but you still see a y here sitting on the skeleton, and if I reduce it, it becomes, again, 2 parallel lines minus 2 crossed lines, and all the junk, all the extra stuff gets copied from in all the diagrams. Okay, but left to right is precisely the 4-term relation. So we just found that the 4-term relation holds in A transpose, and so phi is well defined. So phi is well defined. Okay, now we want to define psi, going backwards. So psi should take a diagram that possibly has trivalent vertices and rewrite it without trivalent vertices. Right? So psi should take, basically, if you have a diagram, if you have a diagram with trivalent vertices and it is connected, then there are 2 possibilities. Either there are no trivalent vertices which are green only, so basically either there are no green only trivalent vertices, in which case it's a core diagram. So so maybe I should write it psi on diagrams with no green vertices. This sounds funny in French. Is itself, right? Because then it's a core diagram and you can just map it to itself. And that actually is the inverse of phi. That would be the inverse of phi. Otherwise, psi acts by, so you will have some trivalent vertex somewhere, a green trivalent vertex, and since the diagram is connected, there will be a green trivalent vertex which is connected to the skeleton somewhere. Okay? So psi will act by using STU to reduce this into the difference of 2 diagrams with 1 trivalent vertex less. Okay? So after that, you just iterate. Okay? The thing to show here is that this is well defined. Okay, so basically I told you that using STU relations you can reduce every diagram in AT to diagrams in ordinary A. But now I have to tell you that this reduction process is well defined. So there are several cases to check. The easiest one is I'll be a bit sketchy. The easiest one is if you have 2 places where you could reduce to the skeleton using an STU relation. So if the green part had 2 places where it was connected to the black skeleton with an edge. Okay, so here you have 2 ways to reduce it. One way will give, so actually let me make all the skeletons in advance. So one way will give this first of all, the uncrossed. So we'll give this minus that, and at the bottom I didn't reduce anything, so it just stays like this. The other way is to reduce it towards the top, towards the bottom, so you'll get at the top the y stays, and at the bottom you get this minus that. Okay? But now let's assume, so I'm not properly setting up the proof, but I could, okay? So let's assume that we've set up the proof to work by induction, and that we claim, and that the argument will be that if a diagram has k green vertices, then its reduction is well defined. So this diagram has k plus 1 green vertices, and I can assume that after I've reduced one, I get diagrams on which the theorem is already proven. So the reduction is well defined. So in particular, I can now reduce using STU the bottom y's, and I'll get now a sum of 4 diagrams, which I will not write down, but I'll only claim that it's but clearly it's the same sum of 4 diagrams that I would get from here. So assuming that in degree that up to k vertices it is well defined, we've just seen that this case in which there are k plus 1 vertices is already well defined. Okay. The next case to check is what if there are, so okay, what if the 2 ways that you want to reduce connect to the same internal vertex? So this was 2 edges along which you wanted to apply STU connect to different internal vertices. But what if they connect to the same one? So here there are still 2 cases to check. So one case is, suppose somewhere in the diagram there was another edge connected to an internal vertex. Okay? Then in this case I would use transitivity. I would say, by what we have just shown, reducing this one or applying STU in this direction is the same as applying STU in this direction, but applying the STU in this direction is equal to applying STU in that direction. So if A is equal to B and B is equal to C, then A is equal to C, and I can claim that I'm done. Okay? The remaining case, the remaining case is, so what remains is a case in which we have a situation like this. So 2 edges connect to the same internal vertex, and then no other connections between an internal vertex and the skeleton. And even this can happen in 2 ways. One way is if this green connects to the skeleton, and there are no other internal vertices. And the other possibility is that this thing connects to some blob, where this blob can be you know, I don't know, can be anything made out of trivalent vertices, but it's not connected to the skeleton other than through the bottom. Okay? So there are two possibilities. Either we connect straight to the skeleton, or we connect to something that that does not connect otherwise to the skeleton. Okay. Here there are genuinely two different ways to apply STU. Okay? So one way is to apply STU to the left, and then you'd get I suppose I'm writing it vertically. So one way would be to apply STU to the left, and you would get this minus that. And the other way would be to apply STU to the right, and you will get this minus that. But these two things are equal by the 4T relation, which was imposed in our target space. We're going backwards now, right? We're going from trivalent to things without trivalent. So this is well defined in our target space. This is, by the way, simply the same argument, or basically it's the same combination of diagrams that I wrote here. I'm sorry about that. Things have gone crazy. It's the same combination of diagrams that I wrote here, but I'm reading it in a different way. Here, when I wrote this the first time, I read it to show that 4T is implied by STU, and now I'm reading it to show that two ways of applying STU give the same answer. But the remaining case is a mess. This case is a mess. In fact, but not such a huge mess, because we've actually done everything. Let me argue to you that this diagram reduces to zero no matter what. Okay? So let's apply the STU relation to the right. Okay? So this is equal to basically the little smiley gets planted on the right, and this edge this edge goes either to this way or that way. It either parallels the base of the smiley, the stem, or goes the other way. Okay? Now we still are within this inductive proof. So now, I mean, here we have k plus 1 internal vertices, now we have k, and we can continue reducing, and the reduction makes sense, is well defined. So I'll do something extremely cruel and collapse the smiley to the skeleton. So the smiley is really here, the smiley really stands for some complicated trivalent diagram, which is not connected to anywhere else except to the stem. But that means that I can collapse it using STUs to the boundary. So the smiley dissolves into some blob of edges. In fact, a linear combination, a blob which contains a linear combination of edges, and the extra edge goes either this way or to the other side of the blob. Right, so the whole smiley collapsed to a blob next to the next to the base of its stem, and here I wrote it magnified, and the extra edge goes either to the left or to the right. Now what?
So there must be something which is zero in algebra, but not working in reducing, right?
I'm sorry. So actually this is something we already dealt with. This minus this is 0 because this was within the proof of commutativity of the commutativity of the product. We've shown that you can slide an edge of a chord across an arbitrary self-contained structure. Okay? Or said it, well, I mean, I could repeat the argument, but basically, well, okay, so basically the assertion was that if you had any blob made out of chords and you had another chords ending this way, then you could move it to the other side. So we've done that. Okay, so the theorem is proven. Now I have to tell you how it's related to Lie algebras, but first I have to tell you a little bit about Lie algebras, and I think I do have to say a few words. Okay, so, or do I? So, you know, let me give a few very, very basic definitions. So, definition, Lie algebra, let's say over a field, is a vector space, let's call it calligraphic G. No, let's call it L for Lie algebra. Along with a bilinear map. So it's called the bracket, and it goes from L squared into L. So in other words, it's a bilinear map. Such that, this bilinear map is antisymmetric. So x bracket y plus y bracket x is equal to 0. And 2, it satisfies the so-called Jacobi identity, so x bracket y bracket z plus all cyclic permutations gives 0. So y bracket z bracket x plus z bracket x bracket y. So this big sum is equal to 0, and this is the so-called Jacobi identity. So in a word, where do Lie algebras come from? So, and I'm not going to prove anything about it, I'm just going to state it. Okay, so if you have some object and you look at its group of symmetries, so sometimes the group of symmetries is discrete. So, you know, if your object is a triangle, then the group of symmetries is or, you know, let's make it more interesting. So if your object is a square, no, a pentagon, then its group of symmetries are rotations and reflections, and the group of symmetries is D5. The dihedral group of order 5, maybe it's called D10 because it has 10 elements, right, there are the 5 rotations and the reflection. Okay? But if the object is continuous, or sometimes the object will have continuous symmetries, and then its group of symmetries will itself be a continuous group. So, for example, if you look at a ball, so if you look at a ball or a sphere, and let's even look at the simple two-dimensional sphere, then the group of rotation, the group of symmetries is the group of rotations, and the group of rotations is the group, well, it's called O3, and O3 is the group of, so let's write it explicitly, what's a rotation? So take an orthonormal basis inside, or put an orthonormal basis to R3, a rotation of the ball would have to carry it to another orthonormal basis. So a matrix that carries an orthonormal basis to an orthonormal basis is a matrix all of whose rows or columns are orthogonal to each other. So if you call this matrix A, the conditions that it satisfies is that A transpose times A is equal to the identity. So O3 is the collection of all matrices A such that A transpose, all 3 by 3 matrices A, such that A transpose times A is the identity. Indeed, if you expand A transpose times A, you find that it's exactly the matrix of inner products. Sorry, I'm going through it very quickly. I hope people have seen it before. Okay? But then in general, you end up looking at other groups of symmetries of objects. So, let me just name a few. So there is SON. So SON is the same thing, but with 3 replaced by N. So it's the group of A, which are N by N matrices with entries in the reals, such that A transpose A is equal to the identity, and in fact that would be just ON, and SON stands for, well, if you look at this, you find that the determinant has to be plus or minus 1, and the S just makes the determinant 1. So you make it orientation preserving rotations. Okay, then there are groups like, okay, then there is, maybe I'll write GL, oh, sorry. So there is GLN. So GLN is simply all invertible matrices. So all invertible N by N matrices. Then there is lots of other examples. Maybe I'll give just one more. So SLN is those invertible matrices whose determinant is 1. So A inside GLN, such that, sorry, I should have used uppercase letters. I'm confused. So this is GLN and this is SLN. So all matrices for which the determinant is equal to 1. So these are clearly interesting. Okay, their group of symmetries are always interesting. And then comes a long discussion which I don't want to carry out, but it's the following. So these groups are all both groups and manifolds. So themselves, right, so this is this is some this is some subset of R to the N squared, or let's look at SON. So N by N matrices live in R to the N squared, and this is some subset of R to the N squared, and you can look at it and see that it's a manifold. And then so schematically, the group itself looks like, so basically the only manifold I can draw is the sphere, so the group itself looks like some manifold. Okay? But it's a very special kind of manifold because all points in it look the same. In the sense that there is a so on a group there is always multiplication from the left by an element, and it takes you from one place in the group to another place in the group, and you can get from any place to any place by multiplying on the left. So in some sense, all points look the same. And then, and again, I'm not being formal about what it means, but what it really means is that that in order to understand the group, it's enough to look at the neighborhood of any individual point. And again, I'm not entirely right. I'm basically trying to motivate the notion of a Lie algebra. Okay? And the neighborhood of any individual point is isomorphic, or looks like the tangent space at that point. And so, if you want to understand a Lie group, it's enough to understand, so enough to understand the tangent space to the group at the unit of the group, at 1. And this is the so-called Lie algebra of the group. So this is the Lie algebra of the group. And then you go through a lot of analysis, or again, sorry, I hope, maybe I shouldn't have gone into it, because I'm saying it so vaguely that it's almost too vague to have a use, okay? But basically, the group structure on the original group ends up inducing the both the vector structure, well, the bracket structure on the Lie algebra. Okay? And I think I'll stop here. Okay? So, but sort of the thing I really wanted to say was that if you study symmetries, you are naturally led to study infinitesimal symmetries, so symmetries which are near the identity, and infinitesimal symmetries are precisely those Lie algebras that were defined here. So these come naturally, they come all over the place in mathematics. Oi, I shouldn't have gone into it, right? Sorry, please tell me that I made a mistake, I shouldn't have gone into it, I should be doing something else. Okay. Well, so let me go on to the next definition. So, definition, so a metric on a Lie algebra, so a metrized or a metric on L is a non-degenerate symmetric invariant bilinear form on L. So let me explain what all of these words mean. So it means a bilinear form, so it means, well, like the bracket, except I'll denote it with angle brackets, and it goes from L tensor L, but it's a bilinear form, it's not a bilinear operation, so the image is in the ground field, and I will assume that the ground field is the rationals. If you want, you can change it to something else. Okay? Symmetric means that, so such that, one, symmetric means that the inner product of x and y is equal to the inner product of y and x. The bracket was anti-symmetric, the metric is symmetric. Invariant means the following. It means that if you have, well, let me write it this way. So z bracket, sorry, the inner product of z bracket x with y plus the inner product of x with z bracket y is always equal to 0. And finally, non-degenerate means the usual thing that non-degenerate means for an inner product. So 3 is non-degenerate, and non-degenerate just means that if x is not equal to 0, then there exists some y such that the inner product of x and y is not 0. Okay? Maybe I'll give examples, and all the examples that I've shown so far come with a non-degenerate inner product like that. So basically, sorry, I didn't even give examples yet for a Lie algebra. So maybe I'll give examples of Lie algebras along with their inner products right away. So examples. So the linear algebra, sorry, the Lie algebra GLN. But now this is lowercase GLN to make it the Lie algebra. So these are simply the n by n matrices with no conditions whatsoever. I need to tell you what is the bracket. So A bracket B is equal to AB minus BA. It's clearly anti-symmetric. We need to verify Jacobi's identity. So it's labor intensive, but essentially trivial. So A bracket BC is equal to A bracket BC minus CB is equal to ABC minus ACB minus BCA plus CBA. And then the other two terms are obtained from this by cyclic permutations. So they're so the right-hand side will also be obtained by cyclic permutations. So I just have to replace A by B, B by C, C by A in every element of the formulas, in each one of the formulas here. So the second terms will be BCA minus BAC minus CAB plus ACB. And then the last term will give, again I have to shift every variable one up, so B will become, so CAB minus CBA minus ABC plus B plus BAC, and now it's just a matter of matching terms. So ABC appears here with a plus and here with a minus. ACB appears here with a minus and here with a plus. Minus BCA appears here with a minus and here with a plus. CBA appears with a plus and with a minus, and so on. So it's a routine verification. And okay, so I've shown that GLN is a Lie algebra. I need to do one more thing, and this is to show, and I need to, so I need to tell you what is the inner product. So the inner product of two matrices A and B is defined to be the trace of AB, just the trace of the product. So this is symmetric because the trace of AB is equal to the trace of BA, so this is equal to B inner product A, and we have to check the identity, the invariance of the inner product. So the invariant of the inner product is the identity C with A bracket B plus the inner product of A with the bracket of C with B should be 0. But this is a routine verification again. So this is here, this is trace of, so CAB.
Do you not want AB transpose because you can have nilpotent matrices?
No, I think wait. Do I need a transpose? No, I don't think so. I think this is okay.
But then this wouldn't be the Frobenius product, isn't that what you were going for?
The what?
Didn't you want something that looks exactly like the standard inner product on Rn square?
No, I wanted this. Let's check it. Let's see if it works, okay?
Okay.
So, wait. Do I want this? No, this is what I want, yes. So for the for SON, you could put the transpose. But I think this is fine. So CAB minus ACB plus the trace of ACB minus ABC, and let's see here, the ACB cancels the ACB, the ABC, by the cyclic property of the trace, cancels the ABC. I think we're good.
But if you want to check non-degeneracy, and you have the matrix 1 minus 1 1 1, this one has trace square 0, right?
But I'm not asserting that the trace squared is equal to, is non-zero.
Okay, the trace of the matrix A square is 0, and that's what we don't want.
Non-degeneracy, what? No, I'm okay with that. Non-degeneracy means for every A not equal to 0, there exists B such that the inner product of A and B is not equal to 0. I'm not asserting that that the inner product of A with itself is not equal to 0.
Oh, okay, I see. Right, okay, sorry, makes sense.
Okay? And this, okay, so this is something that one has to check, but you can check it. Well, we're already 2 minutes late. We started 2 minutes late, so let's quit now and see you on Friday. Okay.